All right. I'll actually start in a few minutes, but everything that could have gone wrong went wrong. The audio was out. My tablet was out. Couldn't find the cable. Whatever. But we're here now. So if you have questions, I know a couple people emailed me, but if you have questions, you can put it either email me also or Teams me or whatever. There's also that chat. If you have a question, like really specific question, just say the number, and that should be it. I'll do the best I can within the next hour or so to cover as much as I possibly can. As a reminder, it's cumulative. There's going to be limits on there. You're going to have to evaluate limits using rationalizing and dividing out. You're going to have to find limits at infinity or at asymptotes. You're going to have to find derivatives in all shapes and sizes and forms, and using the chain rule and arc sine and arc cotangent, all that stuff. Everything that's on the front page of your cover. In terms of derivatives, you're going to have to need to know. And besides that, there's related rates. There is continuity. There is curve sketching. And Newton's method. And I think that just about covers it. If you want more details, go to On Campus, go to the bulletin board. But these questions I have here are the exact ones I gave you. This is on the content library, so if you ever get stuck or something, or are trying to figure out what exactly to do, you can go back to this and actually see my work. If you're watching this, that'll be a little bit ahead of you. That's great. If you're not, you can at least have this like permanently instead of going back to watch the video over and over again. Yeah, so I'll give people like another 2 minutes or so if they need to, if people still didn't get my email or whatever, and then we'll start. Okay, so I had a couple emails that I'll get to first, but I can definitely do questions 28, 85, 28 and 85 part C of 2 at the end. Whatever that means, I'll get to it. The boat and lighthouse problem, I'll at least get you started. I'm not going to do the entire thing, because that was on the test and we went through it. What's a mathematician's favorite ride at the amusement park? I don't know. But I do know math, so that's where we're going to get started. So Luke Mascara emailed me asking me to do 25 to 28 on the other exam review questions. So I'll do that first. Okay. So 25 to 28 says to use logarithmic differentiation to differentiate each function with respect to x. And this is going to be using logarithmic differentiation, so you have to know kind of the properties of logs and what to do. All right, so starting with number 25. We have y is equal to 4x to the 5x. in order to take a log of this, we don't have any specific rule of x to the x power. We have x to the 5th power, we have 5 to the x power, but we don't have x to the x, because that's both exponential and a power rule, and we don't have anything specific to that. So what we're going to do is we're going to take the natural log of both sides, and that'll hopefully split some things up by using the rules of exponents and the rules of logarithms. Okay, so if we take the natural log of y, and because we do that on the left side, we have to do it on the right side, we get this. And that seems like a little messier than what it already is, but we can kind of separate things using the properties of logarithms. Okay, so we can get the natural log of y is equal to the natural log of 4 plus the natural log of x to the 5x. And we can do that because when we have a product on the inside of a log, right, the 4 and the x to the 5th, we can separate that into the sum of two logs with the same base. And then we just keep separating, right? So there's no calculus being done yet. So this is still the natural log of y is equal to the natural log of 4 plus, and another property of log says that if we have an exponent on the inside, we can take that and put it up front. And now we have this, which again looks a little bit messier, but when we take the derivative of this, it's actually way easier. Okay, so if we then take the derivative of both sides, things get simple. All right, so the derivative of natural log of y is 1 over y times dy dx. So there's that implicit differentiation. The derivative of this natural log of 4, that's just a constant, right? The natural log of 4 is going to be some number. It's a constant, so that just goes to 0. And then we have this thing, which is a product of two things. So we have the derivative of 5x, which is 5 times natural log of x, plus 5x times the derivative of natural log of x, which is just 1 over x. And then we can simplify a little bit. So we get 1 over y dy dx is equal to 5 natural log of x plus 5, right? Because these x's are going to cancel. So that's all of the kind of logarithmic stuff. Now we have to finish the implicit differentiation. In order to solve for this thing, we just have to multiply by y on both sides. You didn't miss anything. I just started because it took me forever to get things ready. And at some point I will do a unit circle question. If I just keep reminding me, and I'll do one. Okay, but in order to finish this one, we have to multiply both sides by y. So that's 5 natural log of x plus 5 times y, and y we know is 4x to the 5x. And this whole thing is our answer. Okay, so dy dx is equal to 5 natural log of x plus 5 all times 4x to the 5x. That's our derivative. I'll do one more of these and then I'll move on, because I do like these questions. I know one is definitely going to show up on your test. So I'll do, I mean, they're all pretty similar. I'll do 26, because that's probably the most different of the other three. So 26, and I'll scroll up here in a second once I get a chance. 26 is y is equal to 2x to the power of x squared. And this is going to be really similar, except now we have an x squared instead of a 5x. So I can actually, yeah, no, I'll just do this. Again, we don't have a property for x to the x, so we have to use some kind of logarithmic differentiation. So we want to take the natural log on both sides, and then use those properties of logarithms to separate as much as we can. Okay, so we have a product, right? We have the product of 2 and x to the power of x squared. So this natural log of y is going to be equal to the natural log of 2 plus the natural log of x to the power of x squared. We can separate more. This is a power, so we can take that, put it out front. And everything else past this is the exact same as what we did above. So we want to take the derivative of both sides. So we get 1 over y dy dx is equal to the derivative of natural log of 2, that's just a constant, so that's equal to 0, plus, and then we need the product rule of these two things. So plus the derivative of x squared, that's 2x, times ln of x, plus x squared times 1 over x. And then we just simplify, multiply over the y, and we're going to get an answer. Okay, so we get 1 over y dy dx is equal to 2x natural log of x plus x. So we get dy dx is equal to 2x natural log of x plus x times y, and we know what y is. Y is this whole thing up here. So times 2x to the x squared. And that's our answer. You don't have to distribute that. That's fine as it is. Okay, I want to give people a couple seconds to kind of look at that and make sure it makes sense. If there's no questions on either of these two things, I'll scroll up a little bit so you can see the other two. I think I can zoom out just a little bit. If you don't have questions over either of these two questions, in the next minute or so, I'll move on to those AP questions, and then I'll get to a unit circle problem. On the AP review, if we have time, can we do 76, 85, and 80? Yeah, so Will asked about 85, so we'll do his questions first, and then we'll get to the other ones for you, Luke. So if any constant, so the natural log of any constant will be 0, so like natural log of 6, it will always be 0. The derivative of any constant is 0. Alright, so it doesn't matter what that constant is. If there's no variable attached to it, you know, it's just 5 as opposed to 5x, whatever that constant is, the derivative of that is 0, because there's no rate of change of a constant. Right, so your example was natural log of 6. If we take the derivative of this thing is a constant. So this is just always going to be 0. Natural log of 6 is not 0, but the derivative of natural log of 6 is 0. Okay. I'm going to go to the AP questions. And you were asking about 76. And 85. So we'll go to 76 first. Got it. Cool. We can do that. Okay, the graph of a differentiable function f is shown in the figure above. Which of the following is true? So this is one of those questions where we're given the graph and nothing else about f, and we have to estimate things about the derivative. So if we just kind of take a step back, and think about what the derivative actually is. The derivative is a slope at a point, and it's kind of following the behavior of the graph around that point. Okay, so the derivative of this point right here, I'll do this in different colors so you know what I'm talking about. The derivative of this point right here, it's going to be some positive value. I don't really know what it is, but it's going to be some positive value. The derivative at the center point right here, that's going to be 0, right? It looks like kind of a point of inflection. So that derivative, at least it's going to be horizontal, so it's going to be 0. It's not necessarily a point of inflection, but it could be. But it flattens out, so that derivative, that rate of change is going to be 0 at that point. And then the derivative at this last one is going to be some negative value, right? So positive slope, we have 0 or near 0, but it's pretty close if it isn't. And then we have some negative slope. Okay, not necessarily -1, just negative. So then we just have to order those things. So f prime of -2 will be the greatest, and then f prime of 0, and then f prime of 3. So we should get, so the least will be f prime of 3. That's going to be less than f prime of 0. And that is going to be less than f prime of -2. I hope that makes sense. This is just really asking you to know what a derivative actually means. Okay. So in pink, that you're going up, you're increasing, so your derivative is positive. At that teal color, that greenish color, your slope kind of levels out, so it's about 0. In the orange, you're decreasing, so that means the derivative is negative. So negative is always going to be less than 0, which is always going to be less than a positive number. Also, I thought we could do the derivatives for these because of the a to the u. Luke, that only works if it's a constant to the power of x. On those examples, we had x to the power of x. Is the music staying on for the whole stream? I don't know. I like something on the background. I can mute it for you guys. I don't really care. It's just there. Cool. So that's 76. The other one, 28. Did we do 28? 28. No, we did not. 28 says an isosceles right triangle with legs of length s has area A is equal to 1/2 s squared. At the instant when s is rad 32 centimeters, the area of the triangle is increasing at a rate of 12 square centimeters per second. At what rate is the length of the hypotenuse of the triangle increasing in centimeters per second at that instant? That's a lot. So we have an isosceles right triangle, so let's just draw that real quick. This probably isn't going to look very good because I can't use the tools. So we have S, I'll call this, I don't know, C, just for hypotenuse. Nope, that's an S. Hi, Anthony. At what rate is the length of the hypotenuse? Okay, so we are given the area of this thing is 1/2 s squared. We need to find the rate that the length of the hypotenuse of the right triangle is increasing. So we're trying to find the rate of change of C. So we need to find dc dt. That does not show up in that equation for area. So we need some kind of equation to get C. We have an equation to get C, so let's just try it. We have the Pythagorean theorem, so we have s squared plus s squared is equal to c squared. Actually, just kidding. We got to do something else first. So let's look at what we're given. We're given the equation for area, and we are also given S is rad 32. And we are given the rate of change of area is 12. So we need to kind of combine all that. So I think what we can do is solve for c squared, or solve for c, and then plug that into s. So basically we're going to do a substitution, I think. Let's take the derivative of area first, because I think that's what I should do. So dA dt is going to be equal to 2 times 1/2 times s. So it's just going to be s times ds dt. We have an s, but we do not have a ds dt. So what do we need to do? We need to solve for it. Okay, so we have dA dt, that's equal to 12. We have an s, that's rad 32. And we should be able to solve for ds dt. So 12 over rad 32 is equal to ds dt. I'm not worried about rationalizing right this second. Just know that this is the change of s when s is rad 32. Okay, so that's our ds dt. Now we need an equation with a dc dt so we can actually solve for it. So that equation would be the Pythagorean theorem. So we have s squared plus s squared is going to be equal to c squared. So 2s squared is equal to c squared. So if we take the derivative of this, we get 4s ds dt is going to be equal to 2c dc dt. So things we have and things that we don't have. We have an s that's given to us, that's rad 32. We just found ds dt. That's this thing right here in green. We don't have a c, but that's actually pretty easy to find. Okay, so to find c, again, we'd use that Pythagorean theorem. So 2 times rad 32s. 2 times rad 32 squared is going to be equal to c squared. So that's 64 is equal to c squared, so 8 is equal to c. And now we can just plug stuff in. Okay, I realize I'm a little bit jumbled around, but I'm hoping we can kind of follow along. Okay, so we have all that stuff, we just got to plug it in. So we have 4s, so 4 times rad 32. ds dt, which is 12 over rad 32, which is convenient, because those rad 32s are going to cancel. And that should be equal to 2 times 8, so 16 dc dt. And then we have everything known besides the dc dt, and we just do some algebra, right? So rad 32 and rad 32 cancel. 4 times 12 is 48. We divide by 16 and we get dc dt. 48 over 16 is just 3. So let me kind of rewind and explain what I did. We used this area and the known rad 32 is S to find, and the known rate of change of area to solve for ds dt. Once we have ds dt, we also need a c. So we did that right here. And then we use the Pythagorean theorem and the derivative of that to get 4s ds dt is equal to 2c dc dt. And then it's all just plugging in things that we know and things that we don't. So we're given s is rad 32. We found c using the Pythagorean theorem. We know that's 8. And we found ds dt. We know that's 12 over rad 32. And then we do some algebra. We solve for dc dt. That's a lot. I want to make sure people understand that, so I'm going to give people a couple seconds to ask questions if they want, or ask clarifying questions, or just think about it. That's fine too. Okay, that is 28. We also did 76, so it looks like 85 is the next one. Get another few seconds on this, and then we'll move to 86. All right. Okay, let f be the function defined by f of x is the natural log of x squared plus 1, and let g be the function defined by g of x is equal to x to the 5th plus x cubed. The line tangent to the graph of f at x is 2. Of f at x equals 2 is parallel to the line of tangent to the graph of g at x equals a, where a is a positive constant. What is the value of a? Okay. So let's start with the line tangent to f at x equals 2. So we have f of x. We need this thing. Okay, so basically, two parallel lines are always going to have the same slope. So we need to find the slope of f of x at x equals 2. And then set that thing equal to the derivative of g and see what x we can get out. Okay, so f of x is natural log of x squared plus 1. The derivative of that thing is 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. F prime of 2, which is this thing, that's why we're plugging in 2, is going to be equal to 2 times 2, which is 4, over 4 plus 1, which is 5. Okay, so if we're thinking about the derivative, if we're thinking about the graph of natural log of x squared plus 1, whatever that is, at x equals 2, it has a derivative, it has a slope of 4/5. Now we need to see basically we're going to set this thing equal to the derivative of g of x, and then solve for x. Okay, so g of x is x to the 5th plus x cubed. G prime of x is 5x to the 4th plus 3x squared. And we want to set that equal to 4/5. And solve for x, which is difficult, but not impossible. I'm going to treat this like a quadratic, because we have something squared plus something is equal to something else, right? So 5x, basically we can treat it like this. And then we're just kind of using the quadratic formula or factoring or whatever. I'm going to use the quadratic formula because I don't want to figure out 4/5. So -3 plus or minus the square root of b squared minus 4 times 5 times -4/5 all over -2 times 5, so -10. And this is going to be x squared now instead of just x, because it's a quartic instead of a quadratic. So -3 minus 5, that's -8. -3 plus 5 is 2 over -10. Yeah, you could just find the zeros on your calculator. I just want to show you that it is possible. But yes, you could plug in 5x to the 4th plus 3x squared minus 4/5 into y1, find the zeros. The real one is going to be your answer. Okay, so we got x squared is equal to, so I want to maybe bring that out here. We got x squared is equal to 8/10, and or x squared is equal to 2 over -10. This thing is imaginary, because if we take the square root, we're taking the square root of a negative number, so that can't be it. The only option is the square root of 8/10, so x is plus or minus the square root of 8/10. I don't have a calculator, so give me a second. .894. That's not right. That's how you do it. I'm just trying to figure out where I went wrong. I got C. C is 0.447. Which is half my, yeah. Where did we... So where, we missed a factor of 2 somewhere then. 2a is negative 10. Oh, you know what? I don't know why I have a negative 10 down bottom. That'd be why. So I'll erase everything that's wrong. This is just me being bad at the quadratic formula. This isn't me getting calculus wrong. Negative b, so that's negative 3 plus or minus the square root of 3 squared, which is 9, minus 4 times 5 times negative 4 fifths, over 2a, that's just 10, not negative 10. So we have x squared is equal to negative 3 plus or minus 5 over positive 10. And this will give us 2 different answers. It will give us negative 8 over 10 or 2 over 10. So the negatives were just switched. So x squared is equal to negative 8 tenths, or x squared is equal to 2 tenths. If we take the square root of negative 8 tenths, we get an imaginary number, so that can't be right. So the only other option is x squared is equal to 2 over 10. So x is equal to rad 2 over 10. So rad 2 over 10 is 0.447. Yeah, so I messed up the quadratic formula. I put a negative down bottom when there shouldn't have been, but it is C, so Will, you are correct. Yeah, my bad. I just messed up quadratic formula. Okay, so the other one we wanted to do was question number 80. Wait, this is 88. Did I accidentally do the wrong one? '85 was the one we were supposed to do. I'm sorry. We did 88 though, bonus. And did we do 80? We didn't do 80 yet. 80 is something that we just covered though, so let's do that first real quick. The function f has a first derivative given by f prime is x to the fourth minus x squared minus 8x minus 3. On what intervals is the graph of f concave up? This is pretty much the exact same as our quiz, except we're given more information. So when we're looking for concavity, we are looking for the sign of the second derivative. So we are given the first derivative, we need the second derivative, which this is just a polynomial, this is easy enough. We see when that's 0, and then we test to the left and to the right of both of those. So yeah, we set this equal to 0. This is where I would use a calculator, plug this into y1, find the zeros, test to the left and the right. Or really just see when this is positive and when this is negative. So I'm gonna go to Desmos real quick. Okay, so we get this thing, this graph. That's the graph of f double prime. F double prime is positive from 2 onward. Where'd it go? There it is. So 2 to infinity, that's it. So it's option A. In order to do this by hand, I could use P over Q, so So then our zeros are going to be... we're just going to test those, and we're going to get this following zeros. So x equals -1 is a0, and x equals 2 is a0. And then we fill out kind of our chart, right? But we only have to worry about f prime of x with x is 2 and -1. So we test the left of -2. We test the left of 2. We test the right of 2. We test the left of -1, we test the right of -1. When we test the left, we get a negative number. When we test the right, we also get a negative number. Yeah. And then when we test the right of 2, we get a positive number. So we only have a point of inflection at x equals 2, and past x equals 2, it's going to be concave up. Right, so this is concave up. So if we're thinking about this really, really simply, this is our quiz, but just the second derivative test. Where do you find this question in OneNote? This is in the AP Semester 1 AP exam review questions, and this is number 80. Okay, so we did 80. We did 76 and 80, I think. Gonna scroll up. Yeah, we did 76. We did 80. We did 85. No, we did 86, and we need to do 85. The function g is continuous on the closed interval 1 to 4, with g of 1 is 5 and g of 4 is 8. Of the following conditions, which would guarantee that there is a number c in the open interval 1 to 4, where g prime of c is 1. Okay, so we have some graph. We don't really know what it looks like, but we do know 2 points on it, and we do know that it's continuous. So at 1, we have 5, right? 1 comma 5 is a point. That is this thing right here. So at 1, we get out 5. At 4, we get out 8. So we get this thing, okay? Which would absolutely guarantee that g prime of some number between them is 1. So just the average rate of change here, the slope between those 2 points is going to be 8 minus 5 over 4 minus 1, which is 3 over 3, which is 1. So, we know that g is increasing on average on the closed interval 1 to 4. That's just like, that's given to us. So A can't be right. G is differentiable on the open interval 1 to 4. That's going to end up being the right answer, I think. I haven't gone through the other ones yet. But as long as this graph is continuous and differentiable, right, so there's no like corners or anything, there's going to be guaranteed a slope somewhere along the line that g prime of c is 1. G has a maximum value on the closed interval 1 to 4. That doesn't matter if it's not continuous or it's not differentiable, right? We could have a maximum here, and then right when it's going to equal our slope of 1, it could like curve down, in which case it's not differentiable at that point, so we are not guaranteed a slope of 1 there. G has a maximum value on the closed interval 1 to 4. It could also be a minimum, right? So it could look like this, right? We're still guaranteed a slope of 1 somewhere along these lines. Okay. So that is not necessarily true. The graph of G has at least one horizontal tangent in the open interval 1 to 4. That's not true. We could literally just have the line, and nowhere is there going to be a horizontal tangent on that graph. Okay, so D also can't be true. So our only option is that G has to be differentiable on that open interval in order. So it has to be differentiable and continuous. That's the mean value theorem, which we went over a couple weeks ago. If those two things are true, then we're guaranteed that somewhere within this interval, right, 1 to 4, there has to be a point somewhere in between those 2 points such that the slope at this random point C has to be equal to the average slope between the 2 points. Is stuff like this going to be on the exam? This should be a gimme question. I know that sounds like this is really hard. This shouldn't be that hard of a problem. There's not a lot of calculus going on. It's more of you thinking what continuous means and maximum means and increasing, and you coming up with a counterexample for each one of these things. Okay. Yeah, so it could. This is a good AP question. AP questions like this show up all the time. What about the mean value theorem? That is the mean value theorem. What does differentiable mean? My dude, differentiable means you can take the derivative of it. What about the mean value theorem? The mean value theorem just says that if we have a continuous and differentiable function between 2 points A and B, right, so whatever it looks like, as long as it's differentiable, which means smooth and curved, and you can take the derivative of it, there exists somewhere between A and B, so somewhere between this point and this point, there is definitely a point C such that the derivative at that point is exactly the slope of this green dotted line. Okay. And that would probably exist somewhere like right here. Right, so, well, probably not right there, probably a little bit further down. Probably like right here or something, right? Because at that point, this slope right here is equal to the average slope, the average rate of change between the 2 points. So this question is all about you trying to come up with counterexamples to all these options and seeing which one is true. I know we didn't spend a whole lot of time on the definition of the mean the definition of the mean value theorem. But I think that's a fair question. Okay, that's 85. We just did 80, right? Yeah, and then 76. I didn't mean to belittle asking what differentiable means. Differentiable means you can take the derivative and it's smooth and curved, right? So you can't take a derivative at this point right here because there's a corner. Well, we need to know arc secant, arc cotangent, or arc cosine, or arc cosecant. You're not going to need to know those arcs. You are going to need to know arc sine, arc cosine, and arc cotangent. Or not arc cotangent, arc tangent. You need to know these three. Okay, people were asking about a unit circle problem, and the best unit circle problem that I could come up with that was on here is, There's like the 12e to the t. I don't know which number it is though. I do like 27. 27 is a good question. I'll just let you do with that with what you want. Where's that problem? Here it is. Nope, not that. This one, number 17. 17 is a good question, and that has to do with the unit circle. All right. So particle moves along the x-axis so that at time t is greater than 0, its position is given by x of t is 12e to the negative t times sine of t. What is the first time at t, which the velocity of the particle is 0? So we are given a position equation, and we need to find the velocity equation. So to do that, we take the derivative of that thing. So the derivative of this thing, this is a product. So the derivative of the first times the second plus this first times the derivative of the second. The derivative of the first thing is negative 12e to the negative t. There's a little bit of chain rule going on there. Times sine of t plus 12e to the negative t times cosine of t. So that's our velocity equation. And this question is asking, when is the velocity of this thing equal to 0? So we set this equal to 0 and try and solve this. Okay, so what I'm going to do is I'm going to add over this thing. So when we do that, we get 12e to the negative t times cosine of t is equal to 12e to the negative t times sine of t. Two pretty big things cancel out, because they're the same on both sides. This thing and this thing cancel each other out. And we want to know when cosine of t is equal to sine of t. So we need to think about when the x value of an angle is equal to the y value of an angle. And that happens at pi over 4. And that's it. 3 pi over 4, but it's asking for the first one. So t has to equal 45 degrees, which is pi over 4. So just to explain more. All right, this is our unit circle. We want to know when the y distance is equal to the x distance. And that only happens when we have a 45 degree angle. Right, 45, 45 right triangle. That's the only time that that's going to happen. So I know everyone has seen that at some point, whether that be in geometry or algebra 2. But a 45, 45 right triangle is the only time that cosine is going to be equal to sine. Can we do 83? Where does the negative come from in front of the 12e? So this thing, if we take the derivative of 12e to the negative t, first of all, we can take out the 12. Okay, e to any power, the derivative of e to any power is just e to that power times the derivative of the inside. So we get 12 e to the negative t times the derivative of negative t. Trying to scroll. Just zoom out. So times the derivative of negative t. The derivative of negative t is just negative 1. So we get negative 1, 12e to the negative t. That's where that negative out front. That's where this negative comes from. Can we do 26 and part C of number 2 at the end if we have time? We can do number 26. I'm assuming you mean on the AP questions. 26, great. Okay, so this is like a more specific example of a limit at infinity, but it's still really interesting, at least to me, because it took a little bit of thought. When we're plugging in really, really, really big numbers for x, there's like a hierarchy of things that grow the fastest. So like x is going to grow faster than a constant. X squared is going to grow faster than x. X cubed is going to grow faster than x squared, which is going to grow faster than x, etc. Right, all the way down. Any constant to the power of x, that's going to grow faster than any of those things. Okay, so when we plug in really, really big numbers in for x that go to infinity, e to the x, or any constant to the power of x, grows way, way faster than any x value ever. So when we're plugging in really big numbers for x for this thing, this x really doesn't matter. So kind of what we're doing is we're taking the limit as x approaches infinity of natural log of e to the 3x over x, because that x in the inside of the parentheses is so minuscule compared to everything else that it really doesn't matter. Okay, then we can assume more, but I want to actually do the logarithm. We can take the 3x, put it out front, because that's an exponent inside of a log. Natural log of e is just 1. So we're left with 3x over x. Those x's just cancel, and we're just left with 3. So the limit as x approaches infinity of that entire thing is 3. So what you're required to do in 26, and really a lot of limit problems as they go to infinity, is kind of compare the growth of things. The things that are growing the fastest are the only things that matter. So that x that I have boxed really doesn't matter compared to the e to the 3x. So when we kind of simplify, if that x is so minuscule compared to e to the 3x, really we're just taking the natural log of e to the 3x, which you should be able to simplify, right? And that's going to simplify down to about 3. The other question, number 2 at the end, and part C of number 2. So not that. Is there another number 2? This one. Okay. A snail is traveling along a path, a straight path. The snail's velocity can be modeled by that per minute for 0 to 15 minutes. Find the acceleration of the snail at time t is equal to 5 minutes. So part A, which you're not asking about, but the derivative of velocity is always going to be acceleration, so you take the derivative of that thing for acceleration. That should be easy points. all the time. At what time is the snail's instantaneous velocity equal to its average velocity over the interval 0 to 15? Okay, so this is going to be comparing the derivative at a point and the average rate of change. So the average rate of change is always the slope between 2 points. Okay, so we have the interval 0 to 15. So we need to take, the velocity at 0 minus the velocity at 15 over 0 minus 15, which is just the slope. Okay, so we plug those numbers in. I gotta remember what this is. 1.4 natural log of 1 plus t squared. Is there a plus 1? Yeah, there's 1 plus t squared. Okay, so if we plug in 0, natural log of 1, that's just 0. So this whole thing is 0. So v of 0 is just 0. Yeah, that's right. And then velocity at 15. 15 squared. It's like 7.588. Eight, 9, I guess if we're rounding right. Just plugging in 15 for t squared. Or plugging in 15 for t. So the slope between those 2 points is going to be negative 7.589. Or negative 15. And we want to see when that is equal to... Oh, you know what? This is not a good question. Yeah, okay. You can't do this, because this requires you to get the position equation, which you don't know how to do yet. That's next semester. Yeah, so good. Yeah, you can't do this yet. That makes sense why you're having problems with it. ln of e, the natural log of e is 1. The natural log of 1 is 0. So there's a difference between the natural log of e and the natural log of 1. So Will, you can't do part C on this problem. Can we do 25? As soon as I find it. Yes. Yeah. Okay. The figure above shows the graphs of the functions f and g. If h of x is f of x times g of x, then h prime of 2 is something. Okay, so h of x is f of x times g of x. H prime of x is going to be the derivative of this product, so it's going to be f prime of x times g of x plus f of x times g prime of x. And then h prime of 2 is just plugging in 2 to all this stuff, which doesn't seem like you know a lot, but you do. You know a lot more than you think. So to start, f prime, whenever we're taking a derivative, it's f prime of something, that is the instantaneous slope at that point. F just so happens to be a line. So our slope is constant all the way through. So for this line, no matter where you're at, but definitely 2, we go up 1 and right 2. So the slope everywhere for f is 2. Sorry, is 1/2. Rise over 1. Run. That should be 2. So f prime of 2 is 1/2. G of 2, when we plug in 2 for g, we get 1. So this thing is just 1. Plus f of 2. F of 2 is 2. Alright, so when we plug in 2, we get 2 out. G prime of 2 is the same thing. It's just the slope of this line. So we go down 2, right 1. So that's just -2. So this whole thing, we get 1/2 minus 4. That is 1/2 minus 8. No. Yeah, 8 over 2. So this is -7/2. That's not right. What did I do wrong? F of 2 is 2. Sorry, it's 3. That's what I got wrong. Yeah, -11. Just can't add. Yeah, so -11 over 2 is the answer. We're at an hour 10, so I kind of want to stop. I'll look at 34. Someone asked about 83 too. Did we do 83? We didn't do 83. We'll do 83 and then I'll call it, because this question was asked a while ago and I just skipped over it. Let f be a function with derivative given by this thing. At what value of x does f attain a relative maximum? So in order to find a relative maximum, we see when that derivative is equal to 0. We test to the left of it. We test to the right of it. And if it goes from increasing to decreasing, that's a relative maximum. So you should notice that this has a whole bunch of decimals, usually, and it's not like you're going to have to guess this. This is a calculator-based question. So really, if you wanted to, you could plug this entire thing into y1, I guess this entire thing, and see when it's going from positive to negative. Okay, so I'll get Desmos up and see if I can do that. And we're looking at the interval from -1 to 9, which is... Yeah, okay. So let me try and get a picture of this up. So hold on a second. There it is. Nope. I wanted this somewhere else. Well, this is fine. This is Calc. This is you're gonna be required to have a calculator on this, right? So this is the graph that you will get if you plug in that equation. Okay, and we're looking for between -1 and 9. So between this number and this number, where it's going from increasing to decreasing, where our derivative is going from positive to negative. Okay, so we switch from a positive first derivative to a negative first derivative right here. I don't know what that number is. That's on Desmos somewhere, but it's in your calculator. You would do secant trace 0, left bound, right bound, in between, and you would get that number. That looks like point something. That looks, where are we at? That looks like 0.638. I think that's the closest one. I don't have a graphing calculator on this computer, so I'm just gonna guess that. But that's a calculator one. So plug this thing into Y1 and see when we go from a positive graph to a negative graph. So just where the graph is up top and it switches to on bottom, that's where it's going from increasing to decreasing, which is our maximum. Is that the graph of the derivative? Yeah, that was the graph of the derivative. I think I can, hold on. Can I? Oh, there it is. Yeah. Sorry, this is gonna, yeah, this is the graph of the derivative. I plug this into Desmos, you would plug it into your graphing calculator, and you would see where we go from a positive graph, right? So all of this is positive, and we switch to negative, so decrease. So all of that pink stuff, our actual graph, our F graph, so no primes. All of this positive slope means we're increasing. When we switch to decreasing, that's when that green part is going to come up. So now we're going down. Now our graph is literally just going down. It's decreasing. Where that happens, that's going to be our relative maximum. And again, this is something you should be able to find the 0 of that on your calculator by doing secant trace 0 and then just follow the prompts. I don't know why I'm here in pre-calculus 12 and I have trig functions and a graph test tomorrow. Fantastic. This is, if you're in pre-calculus, hopefully this is somewhere that you get at some point. Okay, this has been going on for a little bit longer, and I started a little bit later, so I'm gonna shut this down now. That takes care of a lot of things. So this, if you want to rewatch this or anything, it's probably easiest to like stay on the stream and just kind of like scroll through the video. In the next couple of minutes, I'll actually, you should just be able to find the link. The link in my email, it should take you directly to the thing. If it doesn't, I'll send out something here in a couple of minutes. Okay. I don't know who Bigfoot Chaser is, but fantastic. Cool. Can I get the email too? Hi, Joe. I don't know your email. I can send it to you if you want me to, but if you just stay on this, it should be fine. WStream, thanks, Coach. You're welcome. I do the best I can. You're welcome also, George Pajalsta. Appreciate you, Mr. Bame, with W stream. W in the chat. Everyone posted W in the chat. Do it. Put W's in the chat. I will make this final impossible if I don't see more, if I don't see less than, or if I see less than 20 dubs. There we go. All right. Okay. I'm gonna close down the stream. Again, if you have questions or anything, you can scroll through this. I'm gonna do my best to be in school at 8 tomorrow. At some point, I have to put air in my tire, but that shouldn't take super long. So 8 to 8:10, I'll be in my homeroom, and you can ask questions. Bro, sounding like the Emperor from Star Wars. Do it. Yeah, that's the point. All right. Thanks, guys. If you have questions again, let me know.